Okay, in this video I'm going to discuss an example that's very similar to example 4.2.1 in the text. That's the first example I go through of maximum likelihood estimation. And before I go into the details of that, I do want to point out that if you printed a copy of the text at the beginning of this course, I had an error here that's not just a typo. Well, it is a typo, but I think it could be confusing. I've now changed it to maximize. Earlier copies of the text on page 48 will say minimize in both of these places, and it should be maximize. So hopefully that'll prevent some confusion from you, if you haven't already been confused by that. And I'm not going to exactly follow example 4.2.1 in the text. That one was fairly general. I just said I had n observations, x1, x2, all the way up to xn. But here I'm going to give specific observations. And I'm going to go back to the German tank problem. And remember that the German tank problem was about trying to estimate how many tanks the Germans have. And the way that we're going to try to estimate that is based on the tanks that we've captured. So let's suppose that we've captured 5 tanks, and the serial numbers are 342, 14, 68, 501, and 392. And what we're going to assume is that the serial numbers are applied consecutively to the tanks, starting at 1, and then the tanks that we captured are randomly chosen from the population of tanks that have been produced by the Germans. And our goal here is to estimate the number of tanks. So what we have here is a random variable that gives a serial number. So I'll say capital X equals the serial number of randomly chosen tank. And by choose, I mean captured, basically. We capture a tank and we assume it's random from the population. And X is going to have a uniform distribution on the set from 1 all the way up to capital N. It's a discrete uniform distribution because the set of all tanks is discrete. There's a finite number of tanks. And our goal here is to estimate N. We've got all these tanks. We don't know how many tanks there are for the Germans. So the method of maximum likelihood says that we want to maximize the following. Okay, the probability that x equals 342, our first observation, times, I'll need to put a dot in here for times, the probability that x equals 14, the second observation, times the probability that x equals 68, that's the third observation, times the probability that x equals 501, times the probability that x equals 392. Okay, so let me put little dots in here. Let's see, there we go. So what this really is the probability that we capture all those tanks in this order. And what we want to do is choose our parameter capital N so that this probability is as large as it can be. Okay, it's the parameter value under which what happened is most likely. Well, in future examples, there will be a lot more computation involved. In this examples, we don't have a whole lot to do. Let me switch to my writing tablet now. Okay, this probability, the probability that x is 342, is just 1 over n, because we have a discrete uniform distribution and there's n possibilities. So it doesn't actually matter what that number is. And it doesn't matter what this number is. That probability is 1 over n. It doesn't matter what this number is, etc. So we want to maximize 1 over n to the power of 5. Well, if we want to maximize 1 over n to the power of 5, that means we choose n to be as small as possible. We know that n has to be positive, so to maximize this fraction, we minimize the denominator. And that's done by minimizing capital N. Well, I can't just choose n to be as small as I would like. In particular, we have to have positive values here because this is a product of probabilities. Notice that our serial numbers all have to be no greater than n. So we know that, for example, 342 is less than or equal to n. And we know 14 is less than or equal to n. We know 68 is less than or equal to n. And we know 501, is less than or equal to n. And we know that 392 is less than or equal to n. So our estimate for n, remember we're going to put a little subscript of e here to indicate estimate. That's just going to be the smallest that n can be and still have this be true. And that's 501. The minimum of those values. Okay. So in this example, it was a little bit simpler than what was in the text, because in the text, both endpoints here were parameters of the distribution. So I had 2 parameters, but it's really the same idea. We end up with something like this, and we want to make that power as small as possible. And this technique is called the method of maximum likelihood. Now it turns out this isn't exactly what was used. This is very close to what was used to estimate the number of German tanks. However, it isn't exactly what was used because if I choose these 5 tanks, that's not really uniformly distributed, because in particular if I chose tank number 342, if that was captured first, it's not also going to be captured second unless the Allies happen to be really generous and let go of or release the tanks that they capture, which I'm sure will not be the case. So you have to use a slightly different distribution. But this is a good approximation, and it's a nice example that's pretty easy to see how the maximum likelihood plays out.